Good morning. I'm having a bad hair day. This is a question that Mr. S has done with you, and I'm going to do this video as a little bit of a resource, perhaps to cement some of the concepts and also something you can come back to. Hopefully it's mildly amusing. And this question is from, to give credit where credit must be given, Mr. John Rochford, Engineering Studies Guides. I will put a link under this video to his publication site. This is not a paid endorsement, but some great questions, and this question especially goes through a lot of different concepts and is an opportunity to take knowledge that you have and apply it to a real situation. So, Mr. Rochford, you rock. Let's get to the question. This question is from page 74 of the aforementioned Rochford textbook, stage 6 workbook for engineering studies, and it's basically a braking system, and that braking system is a class 2 lever. I want you to think of a wheelbarrow, and it's connected to a master-slave cylinder system for braking. So basically what that means is the lever is pushing on a piston, okay, and we've got brake fluid in all of these lines. It's enclosed, it's an enclosed fluid system, okay? So when the piston drives down on this fluid, the pressure increases, and according to Pascal's law, it's pressure is exerted in the same amount in all directions, but what that also means is that when we change the size of our piston, something magical happens, and that's what we'll be discussing in this video for the first part, because this question is asking you to find the velocity ratio, and when you think of velocity ratio, you can probably start thinking about force magnification in a perfect system, or the speed of the system. But let's just think of it, if it's 100% efficiency, it's, you know, how much more force you're going to get out compared to how much you put in, or how little, depending on whether it's less than 1 or greater than 1. But anyway, we'll get on to that. We're going to be looking at the hydraulic system velocity ratio, pressure in the hydraulic system, and then we'll go on to the other bits. But the first part of this question, we're looking at VR of the hydraulic system, and also pressure in the system. So that will be part 1 of this video. Okay, so part 1 of this question is we're trying to calculate the velocity ratio of this system, okay, this hydraulic system. Okay, so we're going over the hydraulic system first, and then we're going to look at the lever system. You could do either or, but this is probably the simplest part of the question at the moment, because you've got to do a bit of trigonometry over here. Okay, so we've got master cylinder of diameter 15 and a slave cylinder 40. So whenever you've got a hydraulic system, if you've got a larger area on the output, okay, it means it's going to magnify the force. Okay, that's the thing you've got to remember. But really all you need to remember is Pascal's law. And Pascal's law, Mr. Pascal, don't we love you, is basically going to be force out over area out is equal to force in over area in. So basically what that's telling you is that the two ratios have to agree with each other, okay? You can change those formulas around and make it force out on force in equals area out on area in, etc., etc. So there's lots of stuff you can do with that equation. The other thing about this question that you will get wrong, because I know I got it wrong the first time I did it, was you've got to remember that you've got 2 areas here, because he said you've got 2 cylinders, so you have to double the area. So if you get an answer that's half the one that's in the back of the book, you've forgotten to do that, okay? So let's do this equation. Let's do this question now. They're asking you for the velocity ratio of of this system. And you've got to remember that basically if you've got a system that's 100% effective, then your velocity ratio equals your mechanical advantage, okay? So, you know, you're probably going to be thinking about, well, I need a distance effort and a distance load to work out my velocity ratio. You can also use your forces, assuming 100% efficiency, okay? So we don't know our forces yet either, do we? So you might be saying, well, how are we going to answer this question? You know that if you change the subject of this equation and we make it force out over force in is equal to, I'm going to make it area just an A out over A in. Okay, so we know that mechanical advantage is force out over force in. Now, if the efficiency is less than 100%, you can't say velocity ratio equals mechanical advantage. Okay, that's something you need to really get your head around. But assuming we have 100% efficiency, we don't know our force out and our force in yet, but we do know our area out and our area in because we're given diameters. Okay, so that symbol that you'll see quite often with a circle with a line through it, okay, get used to the idea that that is diameter, okay? You'll see it on technical drawings, etc., etc. That's diameter, okay? So we're given all the information we need to work out our area out, which is this area here, and our area in, which is this master cylinder, okay? So let's do the calculations and let's see if we get to the same result that we have in the textbook. I'll just get myself a new piece of chalk. Area out. So we know that our area out is our slave cylinder, which is 40, and our radius is going to be 20. So we're going to say pi times 20 squared. But is that our whole area? Do we know if that's our whole area? No, it's not, because we've got two of them. So we need to multiply by 2. That's why you might end up with that half answer rather than the full answer. Times 2. And we're going to divide by our area in, okay, which is pi times 7.5 squared. And so we'll grab our calculator. Pi times 20 squared times 2 divided by bracket pi times 7.5 squared close bracket equals, and you look here, we get an answer of 14.2. So make sure that you, when you divide, that you make sure you get your order of operation correct and everything else. But we end up with a velocity ratio of 14.2. So our first part of our question was asking for a velocity ratio. I'll just get another colour. So we've got our first part of the answer. It's 14.2. So VR is 14.2. Part 1 of the question solved. And we've learnt a little bit on the way, a few things to look out for. For instance, if the area doubles, you'll need to do that. And you also have found a way of calculating a velocity ratio for a hydraulic system. Okay, so if you want a velocity ratio for a hydraulic system, all you need to do is take your area out and divide by your area in. So velocity ratio for a hydraulic system, area out over area in. Pretty simple, okay? One other thing to remember is that because these pi's cancel down, okay, what you could do is you could just take your diameters. So you could take your diameter, which was 40, and say 40 squared times 2 over 15 squared. So for this type of question, if you don't want to deal with pi, we could just as easily have said, and I'll prove it to you here by using the calculator, we could just get our diameters and go 40 squared divided by 20 squared equals, we're going to multiply by 2, don't we? Because the top's 2. 40 squared times 2 equals divided by 40 squared times 2 divided by, and I nearly did 20 on the bottom, 15 squared equals, and the answer is 14.2. So, when you've got a simple hydraulic system like that, and you want to have your velocity ratio, diameter squared out over diameter squared in. Simple. Part 1 of the problem solved. Okay folks, now we're going to work out our velocity ratio for our lever system, okay, over here. And you can see we've got a pivot at the top here, and our load, the force is being generated is in the middle, and our effort's happening at the end. So you should have studied your levers hopefully by now, and you'll know that you know, you've got your load in the middle, that this is like a wheelbarrow, okay? So we know it's class 2, and we know that class 2 levers always have a velocity ratio of greater than 1 because of the way they're set up. You can't ever end up with a distance effort that's shorter than your distance load. So class 2 lever, but why this is a little bit more complex than some of the simple problems you may have done at the beginning is because all the problems we did at the beginning, we did a lot of problems based on our class 1 lever, which we all know is a seesaw, and all of those problems had our forces and our of effort. If we go force effort, force load, all of them were perpendicular to the arm, okay? So that makes life so much easier, okay? We can already see here in this problem that we're dealing with here that we don't have that luxury, okay? So straight away we know that we're in for a bit of a fight with this question. Once you've done this type of question a couple of times though, you'll actually start to understand a few different more complex ideas, and this will set you in really good stead for when you actually have to do truss analysis, okay? So bear with me. Put your thinking caps on because you really do need to think to do this type of problem. And like any engineering problem, at the start, especially if it's a little bit complex, you are forgiven for feeling like you're a dummy, because I have plenty of moments like that. But this question is designed to kind of show you that even a complex system, if you break it down, and you have enough knowledge of different simple ideas, you can put those simple ideas together and come up with a solution, okay? But I will be honest with you, when I first did this question the first time, boy oh boy did I struggle. So don't feel bad that you may be having difficulties, especially with the second part of the problem, but you will get it if you really concentrate. Okay, so what we need to do is, because we don't know, because we aren't given a perpendicular distance, we can still calculate one. Okay, so what we're going to do is we're going to try and work out a perpendicular distance. And we need to use another idea that we all should know, and that is that we talked about transmissibility of forces, and we said that, you know, if I'm applying a force in this direction, okay, I can apply it, as long as it's applied along the same line of force, I can apply it here, or here, or here. It doesn't really matter as long as it's in the same line, okay? So what we're going to do is we're going to take our 45-degree angle, and I'm going to do this in another color, and we're going to just extend it, because what we're trying to do is we're trying to arrive at an angle that's 90 degrees. Okay, so I'm going to extend that line of force using my beautiful orange chalk up. Now sometimes you might have to extend it the other way, okay, but in this instance we need to extend it up, because what we're trying to do is we're trying to arrive at a situation where our distance to the pivot is 90 degrees. So there's our pivot, okay? So now I'm going to draw a line from our pivot point, and we've now got 90 degrees, okay? So, we're being visited by our cat. So we got now got a line that's 90 degrees, okay? So we need to know this distance, okay? We'll call it D. If we find this distance, we've got a force, we've got a perpendicular distance, okay? We can calculate our velocity ratio, because distance load, the perpendicular distance load is given. It's this distance here, because if you look at the load here, right, the distance here to here, because this is our load here, that's what's doing the work, okay, you can see that's a 90-degree angle, and we've already given that distance because it's over here, it's 100, okay, so all we need to do is do some really clever mathematics to work out that unknown, D, okay, so that's what the problem is. So this is where you have to do a little bit of clever maths and manipulation, okay? So that was the first thing you need to do, join your line to there, and then the next thing you needed to do was to actually work out what's going on. You needed to draw another line, okay? And the other line you needed to draw was from here to here. Okay, I'm bald again. You also need to draw a line across here. Now once you've done that, you've done everything you need to calculate your perpendicular distance D, which is our unknown, okay? And you might well be saying, well, you know, how am I going to work that out, okay? What you need to do is you need to know that this triangle here, you know this side, because you're given all the information over here. So this side over here is going to be equal to 350. You know this side here already is 180. So you can use Pythagoras' theorem to calculate this distance here, okay? Once you know that distance there, and you know this is 90 degrees, okay, you can calculate this angle in here, okay, and then you can work out, because there's 180 degrees in a straight line, you can subtract this angle from 45 to get this, okay. So I'm going to stop the video now, and I'm just going to put down some of the working out here, otherwise we're going to be here forever, but I will show you all the working out to get to that answer. But that's the way you're going to get to the point where you can work out this distance here, which is the perpendicular distance, which is what we need to calculate our velocity ratio of the lever system, which is part 2 of the question. So the next step of this situation, once you've drawn in those extra lines that you've got, is we need to find this angle down here, alpha, okay, because we need to find our way into this triangle, okay, so that we can calculate this perpendicular distance. So what I've done is I've created this triangle here. Now we know this distance here is 350, we know this distance here is 180. So what we did was we calculated our hypotenuse here, okay? So we said h squared equals, you know, the two sides squared. We know how to do Pythagoras' theorem, I hope. So we end up with h equals 393.57. So we now know this length, okay? But we don't know this angle yet. But we can work out this angle because we've actually calculated, I've used this knowledge of this triangle here to calculate this angle here, because now that I know my hypotenuse, I can use tan of this angle we don't know, alpha, and I can say it's the opposite over adjacent, okay, tan, 350 over 180 gets me to understanding that this angle here, alpha, is 62.8, okay? And then to calculate beta, all I need to do is I need to say, well, I know that there's 180 degrees in this straight line. I know that's 45, and we now know that's 62.8. So we just have to say, to calculate beta, beta is equal to 180 minus 45 degrees, because we know that's 45, minus 62.8. And that will get us into the triangle that we're trying to find this length that we don't know. So we're going to go 180 minus 45 minus 62.8, and we end up with 72.2 degrees. So now we've got an angle in here, and we know that's 90 degrees because we made it perpendicular. So now we can calculate this angle up here, and we're going to call that, I don't know, we're going to call it gamma. Now if you're not comfortable using Greek letters, just give them normal letters. Just say that's an A, that's a B, and that's a C, okay? It's just so that you know what angle you're talking about, okay? So now we can work out the gamma, this one up here, by using the fact that we have how many degrees in a triangle. Same as in a straight line, 180. So we can say that 180, we're trying to work out gamma, it's 180 minus our angle that we just calculated for beta, 72.2 minus the 90, and that's going to equal 80 minus 72.2 minus 90, it's going to be 17 degrees roughly, yeah, 17.8 degrees. So now we've got an angle up here of 17.8 degrees. So you can see you had to use a little bit of geometry. So all this time that you've been learning geometry, if you're planning on becoming an engineer and thinking, well, when am I going to never need this trigonometry, this angles in a straight line, all that sort of stuff, we'll need it now. So now we've got that angle worked out, it's just a simple matter of using cos to calculate D, because we know that's 17.8 degrees, okay, we know our H, okay, and cos is equal to, so katoa, adjacent on hypotenuse, okay, so we can say to ourselves, for this angle here, we can say cos 17.8 degrees is equal to adjacent, which is the one we don't know, over the hypotenuse, which we did calculate. We calculated our hypotenuse was 393.57 over here. And when we solve for D, we end up with a perpendicular distance of 3, D is going to be equal to 374.8, okay, approximately. So hopefully you can see that little dance we did to get to our point. But the main thing you need to understand with any of these types of questions is you need, if we're calculating velocity ratios, you need perpendicular distances to the pivot. So when everything's nice and horizontal and vertical, simple. When you've got situations where forces are inclined, you're going to have to calculate that perpendicular distance, okay? So now we just need to say, if we're trying to work out our velocity ratio of a lever system, what is our distance effort over our distance load? Okay, so we've got, this is our distance effort, okay, which we calculated. Now we need to work out, and it's being applied here, we've worked out our distance effort. What's our distance load? Well, our load is here, okay, and our perpendicular distance has already been given to us, okay? So all we need to do is take that value of D that we calculated, 374.8, and divide it by this distance here. Okay, so if we say 374.8 divided by 100, because we know that VR, I'll write the equation down here, VR equals distance effort over distance load. Okay, so that's why we've done 374.8 over 100. Okay, and we just need to move our decimal point because we're dividing by 100. Gives us 3.7. So our velocity ratio for this question, for the simple lever, VR equals 3.7. Okay? So I'm not going to say simple because it's a multi-step question and you have to do quite a bit of geometrical manipulation. That would be a hard question in the HSC. Okay? So, but it's really putting to good use your understanding of all these concepts. It's making you use transmissibility of forces, all that sort of stuff. Okay, so we've now done 2 of the solutions. Pause the video, have a good think about how I've constructed these triangles. Get the question out yourself and do these constructions, and you'll be able to see that once you've made these 2 triangles, you can work out this, then you can work out this angle here, then you can work out how many degrees in a straight line, then you can work out how many degrees in a triangle, and you can get to the distance you require. Once you've got the distance you require, you just need to divide by the other distance, okay? Simple as that. Well, as complex as that, as the case may be. But now you've done this type of question, if you do it yourself and really think about it, if you're given a question like this in the HSC, you will be able to answer it, okay? So that is part 2 of the question. Now we need to work out pressure. So I'm going to rub all this out. So pause the video, do your own solution, get to this point in the question, and then I will show you the next part of the question, which is pressure in the hydraulic system. Okay, so the next part of the question is asking for the pressure in the hydraulic system. Okay, this is a really simple question. Once you've got to this point here, this is gift marks. Okay, so we're doing 3, pressure in the hydraulic system. So we're talking about this part of the system. Okay, so we know that pressure is equal to force over area. Okay, a force over our area. And if we want to do it in pascals, PA, pascals, we need force in newtons and we need area in meters squared. Okay, there's ways of playing around with this, but I always like to convert to those units and then do conversions at the end. It makes life simple, it makes life less likely that you're going to make a mistake. So, what's our force into this system here? Okay, do not say it's 300 newtons, because you already know there's a lever that's being having 300 newtons applied to here, and it's being magnified because you had a VR that was greater. Okay, we know our velocity ratio. Velocity ratio for this question is 3.7 of the lever system. Okay, so first thing we're going to do is calculate that force. Okay, so that force is equal to the input force of 300 times 3.7. Okay, because that's what our velocity ratio does. It's a force magnifier. Okay, so we're going to say 300 by 3.7, and we get 1110 newtons. Okay, so we've got the top of our equation for our pressure. Our area, okay, is going to be equal to area of a circle, pi r squared, which is equal to pi times 0.0075 squared, because I've taken 15 millimetre, because whenever you see this without units, it's going to be in millimetres, okay? 15 millimetres, I've halved it to make it 7.5 to get a radius, and then I've converted it into metres by dividing by 1,000, and all I've done is taken my 7.5, and I've gone 1, 2, 3 to move my decimal point 3 places, okay? That's basic primary school stuff. So we end up with, let's do the calculation, pi times 0.0075 squared equals, and it's always important that you actually do these calculations, okay, because you might be getting them wrong because you're doing something wrong on your calculator. So you really need to make sure that you're getting things right. Let's plug all of this into the equation. It'll make things a lot quicker. Okay, so we're going to say pressure, P, is equal to our force, which we've already calculated, 1110 newtons, divided by our area, okay, which was pi times 0.0075 squared, okay? Plug it into our calculator, we go 1110 divided by pi times 0.0075 squared, close bracket, equals, we end up with a really big number in pascals, huge, okay? Let's have a look here, can you see that? Yes. So you could write that down and write pascals after it, but really, that looks like we can divide it by a million, okay? 2, 3, 4, 5, 6, to see if we got megapascals. And when we do that, we end up with 6.28. So we can say P equals 6.28 megapascals, okay, which is a million pascals per megapascal, okay? So that is your pressure, okay? So now we've got a value for pressure in the system, okay? P equals 6.28 megapascals, okay? So we've already got through 3 sections of this question, okay? Next part we're going to look at the velocity ratio of the entire system, okay? So I'm going to rub this all out, so get this all down and we'll go into the next section. We're on the home straight, nearly there. Next part of the question is asking the velocity ratio of the whole system. So we've got velocity ratio of our hydraulic system, we've got our velocity ratio of our simple class 2 lever, and then you're going to work out how to calculate the velocity ratio of the whole system. Now, I'll be honest with you, I used to get confused by this as well. The way to think about it is that each one of these is like a chain, okay? So that's velocity ratio 1, that's velocity ratio 2, and they're linked together, okay? So we've got an input here of force and an output, let's say force here, okay? Force in, and we've got force out, okay? Now, when I first looked at this, I was very, very tempted just to add them together, okay? And if you did that, you would be wrong, okay? And the reason why is because, let's do a really simple system. If this has a velocity ratio of 2, and this has a velocity ratio of 3, okay? What that means is this multiplies the force in by 2, and this multiplies the force in by 3. So if we just put 1 Newton straight in here, okay, 1 Newton, what comes out here? We're going to double it, aren't we? So we're going to end up with 2 Newtons here. And then when we put 2 Newtons into here, we're going to triple it because it's times 3. So you're going to get 2 times 3, and we're going to have 6 out, okay? 6 Newtons coming out, okay? Now if I added those 2 velocity ratios, 2 plus 3, okay, you would get a velocity ratio of 5, which would mean we have 5 coming out. Okay, so that's why you don't add. When you've got a chain of velocity ratios, one feeding into the other, what do? We multiply. Okay, so to answer this question, we've got a velocity ratio in the first part, the hydraulic system. So VR total is going to be equal to 14.2 times 3.7. And that is equal to, because I am too dumb to do the maths, 14.2 by 3.7 is equal to 52.54. VR total 52.54. And just to make sure that Mr. Komenos has not got it wrong, he's going to go to Bob back at the book and make sure that he's got the answer right. Okay, page 74. Okay, total velocity ratio here is 53.25. I would say the biggest problem for me is that I've gone one decimal place rather than two. Okay, so I'm going to say don't worry about that too much. In fact, if you rounded that up, it would be 53. So really, I've probably been a bit lazy in my methodology. I would suggest 2 decimal places is always a good start. Anyway, that's how you do it. So we've got velocity ratio of the whole system now. So we're going to say 52.54. And now they're saying the mechanical advantage if efficiency is 85%. That's the mechanical advantage of the whole system. Okay, so we need to know our formula for efficiency. Okay, and the way I remember this one is, I remember because Mr. Mavrosakis used to teach this subject. I always go MA over VR, and I remember Mavrosakis. But you can do it any way you like, really. But we go efficiency equals MA over VR. Burn it into your memory. Okay, so we've got, and the symbol for efficiency is eta. Okay, that Greek letter. Okay, so it looks a bit like a small n but writ large. Okay, eta. I'm going to write here eta. Okay, so what you need to do is you need to say we've got an efficiency. They've given it to you. They've said the efficiency is 85%. Now, if you're not multiplying by 100, your eta is going to be a decimal. It's going to be 0.85. So it's a percentage expressed as a decimal. 0.85 equals MA over VR. Okay, so we calculated our VR of the whole system at 52.54. So our MA is going to be equal to 0.85 times 52.54. We're just making MA the subject of the equation. Okay, so we get out our trusty calculator and we say 0.85 times 52.5 by 52.54 equals 44.7. So I ended up with a MA 44.7. Now the book probably doesn't agree with that 100% because, like I said, my rounding's a little bit different. But that is how you get to the correct answer. Okay, and then the last bit of the question is force exerted by the disc pads, assuming that 85% efficiency. Okay, so that means our mechanical advantage is now, and remember that our definition of mechanical advantage is force out over force in. Okay, so they're just saying here, what is the force on the brake pads? Okay, we know the force in is 300. Okay, so we're going to say MA equals F out over F in, which is equal to, let's write it down here. We know our, can you see the bottom of the board? Maybe just. We know our mechanical advantage, we calculated in this part of the question here, 44.7. 44.7 equals force out, which is what we're trying to find, over the force in, which is 300. So we're just going to multiply 300 by 44.7, okay, to make force out the subject of the equation. So we're going to say, where am I going to put it? I'm going to put it just here in this box here, okay? just so that I can stand up for a while. My knees are starting to hurt. So we're going to go force out is going to be equal to, we're changing the subject of this equation down here. We're going to make it 300 by 44.7. And we end up with 13,410 newtons, and we're going to convert that to kilonewtons by dividing by 1,000, so it's 13.4 kilonewtons. And that is the whole of the question done. Okay, so please have a go at doing the question yourself. I'm going to have to vacuum up a lot of chalk dust now. Have a go at doing the question yourself. By all means, see Sir. If you see me wandering around, ask me. I'm happy to answer questions as well when I'm around. And just have a go at doing that question systematically from top to finish. I think the sticking point may be somewhere in this area here if you're having trouble with the geometry, okay? But you should have all the maths you need to answer this question, okay, once you break it down, okay? Have fun with that. Hope it helps. And this is obviously a resource that you can come back to when it's time to study all this stuff. See you in the next one.